Welcome back to the Deep Dive Anatomy, where we like to dissect those complex topics and get right to the good stuff, those precious nuggets of knowledge.
Mm-hmm.
So today we're going to be strapping on our gloves and diving into the world of muscles. It's going to be essential knowledge for any budding medical student out there tackling anatomy.
Yeah.
And hey, before we get started, if you're finding this deep dive helpful, hit that like button and subscribe to the Deep Dive channel for more anatomy adventures.
It's funny. Most people just think of like bulging biceps,
Oh, yeah?
or powerful quads when they hear the word muscle.
Right.
But there's a whole universe of muscle tissue beyond those showstoppers,
Yeah.
each with its own unique structure and function.
Okay, so let's start unpacking this muscle mystery.
All right.
I know we have skeletal, smooth, and cardiac muscle to cover,
Yes.
but how can we categorize them in a way that makes sense,
Mm-hmm.
for someone just starting out?
Well, think of it like this. Some muscles we can consciously control, like flexing your fingers to take notes. Those are voluntary. Others, like the muscles churning your stomach right now after that last meal, are involuntary.
Right.
They do their job without you even thinking about it.
So are those categories related to the striated versus smooth distinction I keep hearing about?
Exactly. Skeletal muscle, the kind we can flex and pose with, has these beautiful striations, stripes you can actually see under a microscope.
Wow.
Smooth muscle, on the other hand, lacks those stripes. Hence the name smooth.
Okay, that's starting to make sense, but where does cardiac muscle fit into all of this?
Yeah,
It's the muscle of the heart, so it must be pretty important.
absolutely. Cardiac muscle is unique.
Yeah.
It's striated like skeletal muscle, but involuntary.
Okay.
Rhythmically contracting to keep your blood pumping.
Mm-hmm.
What's fascinating here is that cardiac muscle cells are interconnected,
Okay.
forming a functional syncytium.
What?
Imagine a network of cells contracting as one giant unit, like a synchronized swimming team,
Okay.
performing a heart-stopping routine.
Okay, that analogy actually really helps.
Good.
So we have these different types of muscle,
Yeah,
but they all share a common purpose, which is movement, right?
precisely. But let's zoom in on skeletal muscle for a moment.
Okay.
The kind responsible for those voluntary movements we're so familiar with.
All right.
And here's a little tip for all those anatomy students out there.
Okay.
Paying attention to how skeletal muscles are named can actually give you clues about their location and function.
Oh, I remember struggling with muscle names in anatomy class.
Oh, yeah.
It felt like learning a whole new language.
Totally.
Are you saying there's a method to the madness?
Absolutely. Take the trapezius muscle, for example.
Okay.
Its name comes from its shape resembling a trapezoid.
Okay.
Then you have the gluteus maximus, aptly named for its size.
Right.
The largest muscle in the human body.
Of course.
And how about the flexor digiti minimi?
Okay.
Well, it flexes your pinky finger.
Okay.
The name tells you exactly what it does.
That's actually pretty clever. It's like a built-in anatomy cheat sheet.
Right.
But I'm curious what's happening beneath the surface of these cleverly named muscles.
Yeah.
What's their structure like?
Picture the skeletal muscle is like a well-organized rope made up of bundles of fibers called fascicles.
Okay.
Each fascicle is like a smaller rope within the bigger one,
Mm-hmm.
and each individual fiber is a single muscle cell,
Right.
packed with even smaller units called myofibrils, the real workhorses of contraction.
It's like those Russian nesting dolls, but for muscle structure.
Right.
But how do those tiny myofibrils actually generate the force needed for movement?
Yeah. Seems like magic.
It does.
Imagine this. Within each myofibril, you have these overlapping filaments of proteins
Wait.
called actin and myosin.
Okay.
Myosin acts like tiny rowers pulling themselves along the actin filaments.
Oh, wow.
This pulling action causes the muscle fiber to shorten, leading to contraction.
So it's like a microscopic tug of war happening inside our muscles every time we move.
Exactly. It's
Okay.
called the sliding filament model.
Wow.
And it involves a complex interplay of molecules and energy.
Right.
Calcium ions act like the starting pistol, signaling the myosin rowers to start pulling.
Uh-huh.
And ATP, the energy currency of our cells, provides the fuel for this microscopic workout.
Wow. That's incredibly intricate.
It is.
And speaking of amazing feats of strength, we can't forget about tendons.
Oh, yeah.
They're the unsung heroes connecting those powerful muscles to our bones,
Yeah.
allowing us to move with such precision.
What's fascinating about tendons is their structure.
Okay.
They're composed of tightly packed collagen fibers arranged in parallel,
Uh-huh.
kind of like those steel cables supporting a suspension bridge.
Oh, I see.
This structure gives them incredible tensile strength, meaning they can resist tremendous pulling forces without snapping.
And that strength is why tendon injuries can be so debilitating for athletes, right?
Absolutely.
They're literally tough to tear, but once they do, it's a long road to recovery.
Think about a basketball player landing awkwardly after a jump shot.
Oh, yeah.
Or a tennis player serving with full force. Right. Those sudden, intense forces can overwhelm even the strongest tendons.
So we've delved into the world of skeletal muscle,
We have.
but I'm really curious about smooth muscle.
Okay.
It's often overlooked,
It is.
but it seems like it plays a vital role in keeping our bodies running smoothly, pun intended.
You're right. Smooth muscle is often the unsung hero of the body,
Yeah.
responsible for those involuntary, sustained contractions we don't even notice.
Right.
It lacks those striations we talked about earlier,
Okay.
and its cells are spindle-shaped,
Mhm.
giving it a smooth appearance under the microscope.
So where do we find this stealthy, smooth muscle in action?
Hmm.
What kind of tasks is it handling behind the scenes?
Think about your digestive system.
Okay.
Slowly churning food and moving it through your intestines?
Right.
Or your blood vessels constantly adjusting their diameter to regulate blood pressure?
Wow.
These are just a few examples of smooth muscle working tirelessly to maintain your internal environment.
It's like the ultimate endurance athlete of the muscle world.
I like that.
Always on the job, quietly keeping things moving.
Yeah.
But what happens when smooth muscle malfunctions?
Oh.
Can that lead to serious health problems?
Absolutely. A condition called achalasia, for example, affects the smooth muscle in the esophagus,
Okay.
the tube connecting your mouth to your stomach.
Mm-hmm.
When this muscle loses its ability to relax, properly swallowing becomes incredibly difficult,
Oh, wow.
leading to discomfort and nutritional problems.
That sounds incredibly unpleasant.
Yes.
It really highlights the importance of smooth muscle for everyday functions we often take for granted.
Right.
Okay, ready to shift gears and explore the most unique muscle of all?
Sure.
Cardiac muscle. The beating heart of our muscular system, literally.
Cardiac muscle is truly remarkable.
Yeah.
It shares similarities with skeletal muscle with its striations, but it's completely involuntary, rhythmically contracting to keep blood flowing throughout your body.
Mm-hmm.
It's like a dedicated drummer keeping a steady beat for a lifetime.
I love that analogy.
Good.
So what makes cardiac muscle so special besides its obvious importance for, staying alive?
Well, we touched on this earlier, but the interconnectedness of cardiac muscle cells is crucial.
Okay.
They form a functional syncytium, which means they act as a single coordinated unit.
Right.
Imagine a network of cells all contracting together like a wave sweeping across a stadium.
So it's like one giant muscle cell all working together to pump that precious blood.
Right.
What allows for this incredible synchronization?
Yeah.
It seems almost too complex to even imagine.
The key lies in specialized junctions between the cells called intercalated discs.
Okay.
They act like tiny bridges holding the cells together and allowing for rapid signal transmission. One cell contracts triggering the next, and so on, creating a wave-like contraction that propels blood through the heart.
It's almost like a domino effect. One cell triggers the next, and the whole heart beats in perfect harmony.
Exactly.
But where exactly is this incredible cardiac muscle located within the heart?
Yeah.
Is it distributed throughout the entire organ?
Well, the heart wall has 3 distinct layers:
Okay.
the epicardium, the myocardium, and the endocardium.
Okay.
The myocardium, the middle layer, is where the magic happens.
Right.
It's packed with those interconnected cardiac muscle cells we've been discussing.
And what about those other layers? Do they play a supporting role in this cardiac symphony?
Absolutely. The epicardium is like the heart's protective outer layer,
Okay.
a shield against damage.
Right.
The endocardium in the innermost layer is smooth and thin,
Okay.
lining the heart chambers and ensuring smooth blood flow.
So it's like a well-coordinated team effort, with each layer contributing to the overall function of the heart.
I like that.
This has been an incredible journey through the muscular system so far.
It has.
We've learned about the 3 main types of muscle tissue, how they're structured, and how they function in different parts of the body.
It's truly amazing how adaptable and specialized muscle tissue is, right?
It is.
But here's a final thought-provoking question to ponder. If muscles are the engines of our bodies, what are the fuel sources that power them?
That's a great question.
Yeah.
It makes you realize there's always more to learn, even about something as seemingly familiar as our muscles.
Right.
But before we dive into that, let's take a quick break.
That's good.
Stay tuned. We'll be back soon to explore the energy systems that keep our muscles humming.
It's fascinating to think about how those microscopic engines within our muscles get the energy they need to keep us moving, breathing, and even thinking.
Yeah, it's not as simple as just eating a big meal and expecting those calories to magically fuel our every action, right?
Right, exactly.
Break it down for us. What are the key players in this muscle metabolism game?
Well, the star of the show is a molecule called ATP, or adenosine triphosphate.
Okay.
It's like the energy currency of our cells, storing and releasing energy whenever and wherever it's needed.
So it's like the cash that our muscles use to do their work.
Yeah, you could think of it that way, but ATP isn't just sitting around in our muscles waiting to be used. It's constantly being produced and consumed through a complex web of metabolic pathways.
Okay, I'm sensing a biochemistry lesson coming on. Can you
Yeah.
give us the simplified version for those of us who haven't cracked a textbook in a while?
Sure, think of it like this. Our muscles have different ways of generating ATP depending on the intensity and duration of the activity.
Okay.
For short bursts of energy like sprinting or lifting a heavy weight, muscles rely on a process called anaerobic metabolism,
Got it.
which doesn't require oxygen.
Uh-huh.
But for sustained activities like long distance running or even just maintaining our posture,
Right.
we need aerobic metabolism, which does require oxygen.
So it's like our muscles have different gears depending on the task at hand.
Exactly, a great analogy.
But how do those gears actually work? What's happening at the molecular level to generate that all-important ATP?
Well, in anaerobic metabolism, muscles break down glucose, a type of sugar, without using oxygen.
Okay.
This process is quick but inefficient, producing a byproduct called lactic acid,
Ah, yes.
which can build up in muscles and cause that familiar burning sensation we all feel during intense exercise.
The dreaded lactic acid burn. I know that feeling all too well.
Mhm.
But what about aerobic metabolism? How does that process differ?
Aerobic metabolism is a more efficient but slower way to generate ATP.
All right.
It requires oxygen and can utilize not only glucose, but also fats and even protein as fuel sources.
Oh, wow. So it's more versatile.
Yes, much more. This is why endurance athletes focus on training their bodies to use oxygen efficiently,
Makes sense.
allowing them to sustain activity for longer periods without hitting that lactic acid wall.
So it's like a marathon runner versus a sprinter, each relying on different metabolic strategies to fuel their performance.
Exactly.
But how does all this relate back to the different muscle types we discussed earlier? Do they all use the same metabolic pathways?
That's a great question, and the answer is no, they don't. Skeletal muscle, with its ability to generate both powerful bursts of force and sustained contractions, is quite versatile in its metabolic capabilities. Smooth muscle, on the other hand, primarily relies on aerobic metabolism as it's designed for those long, slow contractions that keep our internal organs functioning smoothly.
Okay, and what about cardiac muscle? It never gets a break, constantly beating to keep us alive.
Yeah.
How does it fuel that relentless activity?
Cardiac muscle is a metabolic champion, primarily relying on aerobic metabolism to meet its high energy demands.
Wow.
It has an incredible capacity to utilize a variety of fuel sources, including glucose fatty acids and even lactate, which other tissues might consider a waste product.
So it's like the heart is a master recycler, squeezing every last bit of energy out of whatever fuel is available.
Exactly. And this metabolic flexibility is crucial for the heart's ability to adapt to different physiological conditions like exercise or stress.
This deep dive into muscle metabolism has been eye-opening.
Yeah.
It's amazing to think about all the complex processes happening at the cellular level just to keep our bodies moving and functioning.
It really is a testament to the incredible design of our bodies.
For sure. But we haven't even touched on the role of nerves in muscle function.
Right.
Without those signals from the nervous system, our muscles would be like cars without drivers, all dressed up with nowhere to go.
Well, think of nerves as the command centers, sending signals to our muscles, telling them when to contract and when to relax.
Okay.
These signals travel along specialized nerve cells called motor neurons, which form connections with muscle fibers at neuromuscular junctions.
So it's like an intricate electrical wiring system transmitting messages from the brain to the muscles.
Good analogy.
But what does that message actually look like?
It's an electrochemical signal,
Okay.
a pulse of electrical activity that triggers the release of neurotransmitters, chemical messengers that bridge the gap between the nerve and the muscle. One of the key players here is acetylcholine,
Right.
a neurotransmitter that binds to receptors on muscle cells, initiating the chain of events leading to muscle contraction.
So it's like a relay race with the electrical signal passing the baton to the chemical messenger, ultimately leading to muscle action.
That's a great way to visualize it.
But what happens if this communication system breaks down? Can that lead to problems with muscle function?
Absolutely. One dramatic example is muscle paralysis,
Oh, wow.
a condition where muscles lose their ability to contract, often due to damage to nerves or disruption of neurotransmitter signaling.
That sounds terrifying. It makes you realize just how fragile this delicate balance between nerves and muscles really is.
And this is why anesthesiologists have to be so careful during surgery. They use muscle relaxants to temporarily paralyze muscles, making it easier to perform procedures.
Right.
But they also have to be able to reverse this paralysis quickly and safely once the surgery is complete.
It's like walking a tightrope, isn't it? They need to achieve just the right level of muscle relaxation without causing any lasting harm. But what about more common muscle problems, like those pesky strains and tears we all experience from time to time? What's happening at the cellular level when we injure a muscle?
Well, muscle strains and tears are basically injuries to the muscle fibers themselves.
Okay.
They can range from microscopic tears to complete ruptures, and the severity of the injury determines how long it takes to heal and what kind of treatment is needed.
So it's like a sprained ankle, but for muscles rest, ice compression and elevation, is that the basic treatment plan for muscle strains as well?
Those are definitely helpful steps in the early stages of healing, but the key to long-term recovery is rehabilitation.
Yeah.
Gradually strengthening and stretching the injured muscle to restore its full range of motion and prevent future injuries.
And that's where physical therapy comes in, right? Those
Yeah.
folks are miracle workers when it comes to helping people regain their strength and mobility after an injury.
Absolutely. Physical therapists play a vital role in guiding patients through the recovery process, tailoring exercises and treatments to their specific needs, and ensuring they regain full function.
And this brings us to another important concept, muscle atrophy. It's the use it or lose it principle applied to our muscles, right?
You got it. Muscle atrophy is the wasting away of muscle tissue, often due to lack of use, nerve damage, or certain medical conditions.
So it's like muscles need a reason to exist, a purpose to fulfill. If we don't challenge them regularly, they shrink and weaken.
That's a great way to put it. And this is why it's so important to stay active throughout our lives.
Yeah.
Engaging in activities that challenge our muscles and keep them strong and healthy. It's incredible to think that all of these complex processes, from the sliding filament model to the intricacies of muscle metabolism, are happening within our bodies every second of every day.
It really is mind-boggling. And we've only just scratched the surface of this vast and fascinating topic.
Yeah.
But before we wrap up, I wanted to circle back to something you mentioned earlier, those clinical correlations.
Okay.
What are some real-world examples of how muscle dysfunction can impact people's lives?
Well, we've already touched on muscle paralysis and the critical role of anesthesiologists in managing that during surgery.
Right.
But muscle disorders can manifest in many ways, from relatively common conditions like muscle strains and cramps to more serious diseases like muscular dystrophy.
Muscular dystrophy, that's a group of genetic disorders that cause progressive muscle weakness and degeneration, right?
Exactly. It's a heartbreaking condition that highlights the crucial role of proteins like dystrophin in maintaining the structural integrity of muscle fibers.
Okay.
Without these proteins, muscle cells become fragile and susceptible to damage, leading to gradual loss of muscle function.
So it's like the scaffolding that holds the muscle together is weakened or missing, making the entire structure vulnerable to collapse. Are there any effective treatments for muscular dystrophy?
While there's no cure for muscular dystrophy, research is ongoing, and there are promising therapies that can help manage symptoms, slow progression, and improve quality of life.
Okay.
Gene therapy, for example, holds great potential for addressing the underlying genetic defects that cause the disease.
It's amazing how far medical science has come in understanding and treating these complex muscle disorders.
It really is.
But even for those of us lucky enough to have healthy muscles, it's important to remember that they need care and attention, just like any other part of our body.
Absolutely. Regular exercise, a balanced diet, and proper hydration are essential for maintaining muscle health throughout our lives.
Right.
And for those who are more athletically inclined, proper warm-up stretching and gradual training progression can help prevent injuries and keep those muscles firing on all cylinders.
This deep dive into the world of muscles has been a truly enlightening experience.
Yeah.
I feel like I've gained a whole new appreciation for these incredible tissues that allow us to move, breathe, and live our lives to the fullest.
Me too. It's been my pleasure to share my knowledge and passion for this topic with you and our listeners.
And a huge thank you to all our listeners for joining us on this anatomical adventure. We hope you found this deep dive informative and engaging.
Yes, thank you.
Don't forget to like and subscribe to the Deep Dive channel for more fascinating explorations into the human body and beyond.
And until next time,
Keep those muscles moving and those brains engaged. Thanks for listening to The Deep Dive.